Hello, folks, and welcome. Welcome to another episode of ML for Noobs. This time, we're finally diving into lesson three. Lesson three of 7 lessons as part of this Fast AI course, the 2019 edition. That said, this lesson is going to be about data blocks, multi-label classification, and segmentation. I have no idea what any of that means, but I can't wait to find out. Jeremy, take it away.
Welcome back to lesson 3. So we're going to start with a quick correction, which is to let you know that when we referred to this chart as coming from Quora last week, we were correct. It did come from Quora, but actually we realized originally it came from Andrew Ng's excellent machine learning course on Coursera. So apologies for the incorrect citation. In exchange, let's talk about Andrew Ng's excellent machine learning course on Coursera. It's really great. As you can see, people gave it 4.9 out of 5 stars. In some ways, it's a little dated, but a lot of the content really is as appropriate as ever and taught in a more bottom-up style, so it's going to be quite nice to combine Andrew's bottom-up style and our top-down style and meet somewhere in the middle. Also, if you're interested in more machine learning foundations, you should check out our machine learning course as well. If you go to course.fast.ai and click on the machine learning button, that will take you to our course, which is about twice as long as this deep learning course and kind of takes you much more gradually through some of the foundational stuff around validation sets and model interpretation and how PyTorch tensors work and stuff like that. I think all these courses together, if you want to really dig deeply into the material, do all of them, and a lot of people who have and end up saying, oh, I got more out of each one by doing the whole lot, where you can skip backwards and forwards, see which one works for you. So we started talking about deploying your web app last week. One thing that's going to make life a lot easier for you is that on the Course V3 website, there's a production section where right now we have one platform, but more will be added by the time the video comes out, showing you how to deploy your web app really, really easily. And when I say easily, for example, here's the how to deploy on Zeit guide created by San Francisco study group member Nebjot. As you can see, it's just a page. There's almost nothing to do, and it's free. It's not going to serve 10,000 simultaneous requests, but it'll certainly get you started, and I found it works really well. It's fast, and so deploying a model doesn't have to be slow or complicated anymore. And the nice thing is you can kind of use this for an MVP, and if you do find you're starting to get 1,000 simultaneous requests, then you know that things are working out, and you can start to upgrade your instance types or add to a more traditional big engineering approach. So if you
I was wondering how you could actually push this out to the web. I mean, I had it running locally, but I'll be honest, like I actually tried deploying this on Heroku and Friends. It didn't really work that well. There were a lot of dependency issues and juggling a bunch of stuff around pip packages and requirements. And so I really want to try this out, probably at the end of this lesson or maybe next lesson.
actually use this starter kit, it will actually create my teddy bear finder for you. And this is an example of my teddy bear finder. So the idea is it's as simple as possible, this template. So you can fill in your own style sheets, your own custom logic, and so forth. This is kind of designed to be a minimal thing so you can see exactly what's going on. The back end is a simple kind of REST style interface that sends back JSON. And the front end is a super simple little JavaScript thing. It should be a good way to get a sense of how to build a web app which talks to a PyTorch model. So examples of web apps people have built during the week. Edward Ross built the What Car Is That app, or more specifically the What Australian Car Is That. I thought it was kind of interesting that Edward said on the forum that the building of the app was actually a great experience in terms of understanding how the model works himself better. And I guess it's interesting that he's describing like trying it out on his phone. A lot of people think like, oh, if I want something on my phone, I have to create some kind of mobile TensorFlow, ONNX, whatever tricky mobile app. You really don't. You can run it all in the cloud and make it just a web app, or use some kind of simple little GUI front end that talks to a REST backend. It's not that often that you need to actually run stuff on the phone. So this is a good example of that. C. Werner has created a guitar classifier. You can decide whether your food is healthy or not. Apparently this one is healthy, that can't be right. I would have thought a hamburger is more what we're looking for, but there you go. Apparently Trinidad and Tobago is the home of a hummingbird, so if you're visiting, you can find out what kind of hummingbird you're looking at. You can decide whether or not to eat the mushroom. If you happen to be one of the cousins of Charlie Harrington, you can now figure out who is who. I believe this was actually designed for his fiancée. Even will tell you about the interests of his particular cousin. So, fairly niche application, but apparently there are 36 people who will appreciate this at least. I have no cousins. That's a lot of cousins. This is an example of an app which actually takes a video feed and turns it into an emotion classifier. That's pretty cool. I like it. Team 26, good job. Here's a similar one for American Sign Language. And so it's not a big step from taking a single image model to taking a video model. You can just grab the occasional frame, put it through your model, and update the UI as the kind of model results come in. So it's really cool that you can do this kind of stuff either in client or in browser nowadays. Henry Polacci has built Your City From.space, which he describes as creepy, how accurate it is. So here's where I live, which I figured out was in the United States. It's interesting, he describes here how he actually had to be very thoughtful about the validation set he built, make sure that the satellite tiles were not overlapping or close to each other. In doing so, he realized he had to download more data, but once he did, he got this amazingly effective model that can look at satellite.
Yeah, I can understand how this would work with classifiers, right? Just generally trying to classify things. But I can't understand how this would actually work with the sort of things that he's describing. So, okay, sign language, I get that. That could work. Emojis, I suppose that could work too if you have like a fixed set. Angry, happy, smiling, whatever it is. That could actually work. But this, this Your City From, how would that work? Like unless you have a bunch of countries, and not all the countries. All right, so he says download data from the largest 25,000 cities in the world. Around 100,000 labeled images in the wow. Okay. Where did he get this data from? Huh. That's very interesting. Okay.
Country and figure out what country it's from. I thought this one was pretty interesting, which was doing univariate time series analysis by converting it into a picture using something I've never heard of, a gradient angular field. But he says he's supposed to say the results for univariate time series modeling by turning it into a picture. And so I like this idea of turning stuff that's not a picture into a picture. So something really interesting about this project, which was looking at motion classification from faces, was that he was specifically asking the question, how well does it go without changing anything, just using the default settings? Which I think is a really interesting experiment, because we were all told it's really hard to train models and it takes a lot of specific knowledge, and actually we're finding that that's often not the case. And he looked at this facial expression recognition dataset. There was a 2017 paper that he compared his results to, and he got equal or slightly better results than the state-of-the-art paper on motion recognition without doing any custom hyperparameter tuning at all. So that was really cool. And then Lina Harley, who I featured one of her works last week, has another really cool work in the genomic space, which is looking at variant analysis, looking at false positives in these kinds of pictures, and she found she was able to decrease the number of false positives coming out of the kind of industry standard software she was using by 500% by using deep learning workflow. I think this is a nice example of something where if you're going through, spending hours every day looking at something, in this case looking at trying to get rid of the false positives, maybe you can make that a lot faster by using deep learning to do a lot of the work for you. And again, this is an example of a computer vision-based approach on something which initially wasn't actually images. So that's a really cool application. So really nice to see what people have been building in terms of both web apps and as classifiers. What we're going to do today is look at a whole lot more different types of models that you can build. And we're going to kind of zip through them pretty quickly, and then we're going to go back and say, like, oh, how did all these things work? What's the common denominator? But all of these things, you can create web apps from these as well, but you'll have to think about how to slightly change that template to make it work with these different applications. I think that'll be a really good exercise in making sure you understand the material. So the first one we're going to look at is a data set of satellite images. And satellite imaging is a really fertile area for deep learning. It's certainly a lot of people already using deep learning satellite imaging, but only scratching the surface. And the data set that we're going to look at looks like this. It has satellite tiles, and for each one, as you can see, there's a number of different labels for each tile. One of the labels always represents the weather that's shown, so in this case, cloudy or partly cloudy. And then all of the other labels tell you any interesting features that are seen there. So primary means primary rainforest, agriculture means there's some farming, road, and so forth. So as I'm sure you can tell, this is a little different to all the classifiers we've seen so far, because there's not just one label, there's potentially multiple labels. So multi-label classification can be done in a very similar way. But the first thing we're going to do is to download the data. Now this data comes from Kaggle. Kaggle is mainly known for being a competitions website, and it's really great to download data from Kaggle when you're learning, because you can see how well I've gone in that competition, and it's a good way to see whether you kind of know what you're doing. I tend to think the goal is to try and get in the top 10%. In my experience, all the people in the top 10% of the competition really know what they're doing. So if you can get in the top 10%, then that's a really good sign. Pretty much every Kaggle dataset is not available for download outside of Kaggle, at least the competition datasets, so you have to download it through Kaggle. The good news is that Kaggle provides a Python-based downloader tool, which you can use. So we've got a quick description here of how to download stuff from Kaggle. So to install stuff, to download stuff from Kaggle, you first have to install the Kaggle download tool, so just pip install Kaggle. And so you can see what we tend to do when there's one-off things to do is we show you the comment about version in Notebook, and you can just remove the comment. So here's a cool tip for you. If you select a few lines and then hit Control/, it uncomment them all, and then when you're done, select them again, Control/ again, and recomment them all. Okay? So if you run this line, it'll install Kaggle for you. Depending on your platform, you may need sudo, you may need /something else, /pip, you may need source activate. So have a look on the setup instructions, actually the returning to work instructions on the course website to see, like, when we do conda install, you have to do the same basic steps for your pip install. So once you've got that module installed, you can then go ahead and download the data. And basically, it's as simple as saying Kaggle competitions download, the competition name, and then the files that you want. The only other steps before you do that is that you have to authenticate yourself. And you'll see there's a little bit of information here on exactly how you can go about downloading from Kaggle the file containing your API authentication information. So I won't bother going through it here, but just follow these steps. Sometimes stuff on Kaggle is not just zipped or tied, but it's compressed with a program called 7-zip, which will have a 7z extension. If that's the case, you'll need to either apt install p7zip, or here's something really nice. Some kind person has actually created a Conda installation of 7-zip that works on every platform. So you can always just run this Conda install, doesn't even require sudo or anything like that. And this is actually a good example of where Conda is super handy, is you can actually install binaries and libraries and stuff like that, and it's nicely cross-platform. So that's good. If you don't have 7-zip installed, that's a good way to get it. And so this is how you unzip a 7-zip file. In this case, it's tied and 7-zip, so you can do this all in one step. So 7zip is the name of the 7-zip archive program that you would run. Okay, so that's all basic stuff, which if you're not so familiar with the command line and stuff, it might take you a little bit of experimenting to get it working. Feel free to ask on the forum. Make sure you search the forum first to get started. Okay, so once you've got the data downloaded and unzipped, you can take a look at it. So in this case, because we have multiple labels for each tile, we clearly can't have a different folder for each image telling us what the label is. We need some different way to label it. And so the way that Kaggle did it was they provided a CSV file that had each file name, along with a list of all of the labels. In order to just take a look at that CSV file, we can read it using the pandas library. If you haven't used pandas before, it's kind of the standard way of dealing with tabular data in Python. It pretty much always appears in the PD namespace. In this case, we're not really doing anything with it other than just showing you the contents of this file. So we can read it, we can take a look at the first few lines, and there it is. So we want to turn this into something we can use for modeling. So the kind of object that we use for modeling is an object of the data bunch class. So we have to somehow create a data bunch out of this. Once we have a data bunch, we'll be able to go .show batch to take a look at it, and then we'll be able to go create CNN with it, and then we'll be able to start training. Okay? So really the trickiest step previously in deep learning has often been getting your data into a form that you can get it into a model. So far, we've been showing you how to do that using various factoring methods. So methods where you basically say, I want to create this kind of data from this kind of source.
Okay, let me just open this up, make sure I've got this going. Just so we're on the same page. Jeremy's really flying through that one. Alright, pip install. Let's run that. Then we'll need to run this. Yeah, let's just wait for this to finish. Is that done? Successfully installed. Then you need to upload your credentials, log into Kaggle, click on your profile picture, My Account, scroll down, create new API token, upload this file to the directory this notebook is running in by clicking upload, then uncomment and execute the next two commands. Alright, so I hadn't done that. I can go ahead and do that. Alright, so at this point I uploaded my Kaggle JSON file that's moved into one of the directories after I ran the command. And now I should be able to just go ahead and download the competition data. I had to accept the terms and conditions related to competition on the Kaggle website. So now it's got that downloaded, and let's wait and see. Looks like it's it looks like it's about done. And at this point, we can just go ahead and do run this to install 7-zip. This might take a few minutes to complete. Okay, so that one's still running. Let's just run that while, as soon as that's done, and then we should be able to uncomment all of this. Alright, cool. So we're just going to wait until this is done unzipping all of our data. Or actually it should be done installing 7-zip first. So that's done. And now it should be able to unzip all that stuff. Let's play the video.
With these kinds of options. The problem is, that works fine sometimes, and we showed you a few ways of doing it over the last couple of weeks. So far, we've been showing you how to do that using various factoring methods. So methods where you basically say, I want to create this kind of data from this kind of source with these kinds of options. The problem is, that works fine sometimes, and we showed you a few ways of doing it over the last couple of weeks. But sometimes, you want more flexibility, because there's so many choices that you have to make about where do the files live, and what the structure they're in, and how do labels appear, and how do you spit out the validation set, and how do you transform it, and so forth. So we've got this unique API that I'm really proud of called the DataBlock API. And the DataBlock API makes each one of those decisions a separate decision that you make. There's separate methods and with their own parameters for every choice that you make around how do I create, set up my data. So for example, to grab the planet data, we would say we've got a list of image files that are in a folder, and they're labeled based on a CSV with this name. They have this separator. Remember I showed you back here that there's a space between them? So if I pass in the separator, it's going to create multiple labels. The images are in this folder. They have this suffix. We're going to randomly spit out a validation set with 20% of the data. We're going to create data sets from that, which we're then going to transform with these transformations. And then we're going to create a data bunch out of that, which we'll then normalize using these statistics. So there's all these different steps. So to give you a sense of what that looks like, the first thing I'm going to do is going to go back and explain what are all of the PyTorch and FastAI kind of classes that you need to know about that are going to appear in this process, because you're going to see them all the time in the FastAI docs and the PyTorch docs. So the first one you need to know about is a class called a dataset. And the dataset class is part of PyTorch. And this is the source code for the dataset class. As you can see, it actually does nothing at all. The dataset class in PyTorch defines three things: get, item, and len. In Python, these special things are underscore, underscore something, underscore, underscore. Pythonisters call them dunder something. So this would be dunder, get, item, dunder, len. And they're basically special magical methods that do some special behavior. And this particular method, you can look them up in the Python docs. This particular method means that your object, if you had an object called O, can be indexed with square brackets. Something like that. Right? So that would call get item with 3 as the index. And then this one called len means that you can go len, O, and it will call that method. Now you can see in this case, they're both not implemented. So that is to say, although PyTorch says to tell PyTorch about your data, you have to create a data set, it doesn't really do anything to help you create the data set. It just defines what the data set needs to do. So in other words, your data, the starting point for your data, is something where you can say, what is the third item of data in my data set? So that's what an item does, and how big is my data set? That's what the length does. So FastAI has lots of dataset subclasses that do that for all different kinds of stuff. And so far, you've been seeing image classification datasets. So they're datasets where get item will return an image and a single label of what is that image. So that's what a data set is. Now, a data set is not enough to train a model. The first thing we know we have to do, if you think back to the gradient descent tutorial last week, is we have to have a few images or a few items at a time so that our GPU can work in parallel. And we do this thing called a mini batch. A mini batch is a few items that we present to the model at a time that it can train from in parallel. So to create a mini batch, we use another PyTorch class called a data loader. And so a data loader takes a data set in its constructor. So it's now saying, oh, this is something I can get the third item and the fifth item and the ninth item. And it's going to grab items at random and create a batch of whatever size you ask for and pop it on the GPU and send it off to your model for you. Right? So a data loader is something that grabs individual items, combines them into a mini batch, pops them on the GPU for modeling. So that's called a data loader, and that comes from a data set. So you can see already there's kind of choices you have to make. What kind of data set am I creating? What is the data for it? Where does it come from? And then when I create my data loader, what batch size do I want to use? Right? This still isn't enough to train a model. Not really, because we've got no way to validate the model. If all we have is a training set, then we have no way to know how we're doing because we need a separate set of held out data, a validation set, to see how we're getting along. So for that, we use a FastAI class called a data bunch. And a data bunch is something which, as it says here, binds together a training data loader and a valid data loader. And when you look at the FastAI docs, when you see these kind of monospace font things, they're always referring to some symbol you can look up elsewhere. So in this case, you can see trainDL is here. And there's no point knowing what there's an argument with a certain name unless you know what that argument is. So you should always look after the colon to find out that is a data loader. Okay, so when you create a data bunch, you're basically giving it a training set data loader and a validation set data loader. And that's now an object that you can send off to a learner and start learning. Right? So they're the basic pieces. So coming back to here, this stuff, plus this line, is all the stuff which is creating the data set. So it's saying where do the images come from? Because the data set, the index returns two things. It returns the image and the labels, assuming it's an image data set. So where do the images come from, where do the labels come from, and then I'm going to create two separate data sets, the training and the validation. This is the thing that actually turns them into PyTorch data sets. This is the thing that transforms them. Okay, and then this is actually going to create the data loader and the data bunch in one go. So let's look at some examples of this data block API, because once you understand the data block API, you'll never be lost for how to convert your data set into something you can start modeling with. So here's some examples of using the data block API. So for example, if you're looking at MNIST, which remember is the pictures and classes of handwritten numerals, you can do something like this. What kind of data set is this going to be? It's going to come from a list of image files, which are in some folder, and they're labeled according to the folder name that they're in. And then we're going to split it into training and validation according to the folder that they're in, training and validation. You can optionally add a test set. We're going to be talking more about test sets later in the course. Okay, we'll convert those into PyTorch data sets now that that's all set up. We'll then transform them using this set of transforms. And we're going to transform into something of this size, and then we're going to convert them into a data bunch. So each of those stages, inside these parentheses, are various parameters you can pass to customize how that all works, right? But in the case of something like this MNIST data set, all the defaults pretty much work, so this is all fine. So here it is, so you can check. Let's grab something. So data.trainDS is the data set, or the data loader, the data set, so I can actually index into it with a particular number. So here is the zero indexed item in the training data set. It's got an image and a label. We can show batch to see an example of pictures of it, and we can then start training. So here are the classes that are in that data set. And this is a little cut down sample, then this just has 3s and 7s. Here's an example using Planet. This is actually again a little subset of Planet we'll use for make it easy to track things out. In this case, again, it's an image file list. Again, we're grabbing it from a folder. This time we're labeling it as a CSV file. We're randomly splitting it. Default is 20%. Creating data sets, transforming it using these transforms. We're going to use a smaller size and create a data bunch. There it is. And so data bunches know how to draw themselves, amongst other things. So here's some more examples we're going to be seeing later today. What if we look at this data set called Canvid? Canvid looks like this. It contains pictures, and every pixel in the picture is color-coded. Right? So in this case, we have a list of files in a folder, and we're going to label them, in this case, using a function. And so this function is basically the thing you're going to see later, which tells it whereabouts the color coding for each pixel is in a different place. Randomly split it in some way, create some data sets in some way. We can tell it for our particular list of classes, how do we know what pixel value 1 versus pixel value 2 is, and that's something that we can basically read in, like so. Again, some transforms, create a data bunch, you can optionally pass in things like what batch size do you want, and again, it knows how to draw itself, and it's that. Or one more example, what if we wanted to create something like this that has like bars and share and remote control and book. This is called an object detection data set. So again, we've got a little minimal COCO data set. COCO is kind of the most famous academic data set for object detection. we can create it using the same process. Create a list of files from a folder, label them according to this little function, randomly split them, create an object detection dataset, create a data bunch. In this case, as you'll learn, when you get to object detection, you have to use generally smaller batch sizes, so you run out of memory. And as you'll also learn, you have to use an calculation function. And once that's all done, we can again show it, and here's our object detection dataset. So you get the idea, right? So here's a really convenient notebook. Where will you find this? This notebook is the documentation. Remember how I told you that all of the documentation comes from notebooks? You'll find them in your FastAI repo in docs_source. So this, which you can play with and experiment with inputs and outputs and try all the different parameters, you'll find the Datablock API examples of use. If you go to the documentation, here it is, the Datablock API examples of use. Right? So remember, everything that you want to use in FastAI, you can look it up in the documentation. So let's search Datablock API. Goes right there. And away you go. And so once you find some documentation that you actually want to try playing with yourself, just look up the name, Datablock, and then you can open up a notebook with the same name in the FastAI repo and play with it yourself. Okay. So that's a quick overview of this really nice Datablock API, and there's lots of documentation for all of the different ways you can label inputs and split data and create data sets and so forth. And so that's what we're using for Planet. Okay, so we're using that API. You'll see, like in the documentation, these two steps we had all joined up together. We can certainly do that here too, but you'll learn in a moment why it is that we're actually splitting these up into two separate steps, which is also fine as well. So a few interesting points about this. Transforms. So transforms by default, maybe you can hit Shift-Tab to get all the information, right? Transforms by default will flip randomly each image, right? But they'll actually randomly only flip them horizontally, which makes sense, right? If you're trying to tell us something's a cat or a dog, it doesn't matter whether it's pointing left or right, but you wouldn't expect it to be upside down. On the other hand, satellite imagery, whether something's cloudy or hazy, or whether there's a road there or not, could absolutely be flipped upside down. There's no such thing as a right way up from space. So flip vert, which defaults to false, we're going to flip over to true to say, like, yeah, randomly, we should actually do that. That doesn't just flip it vertically, it actually tries also 8 possible 90-degree rotations. So there are 8 possible kind of symmetries it tries out. So there's various other things here. I found that these particular settings work pretty well for Planet. One that's interesting is warp. Perspective warping is something which very few libraries provide, and those that do provide it tends to be really slow. I think FastAI is the first one to provide really fast perspective warping. Basically, the reason it's interesting is if I kind of look at you from below versus look at you from above, the kind of your shape changes, right? And so when you're taking a photo of a cat or a dog, sometimes you'll be higher, sometimes you'll be lower, then that kind of change of shape is certainly something that you would want to include as you're creating your training batches. You want to modify it a little bit each time. Not true for satellite images. A satellite always points straight down at the planet. So if you add perspective warping, you'll be making changes that aren't going to be there in real life. So I turn that off. So this is all something called data augmentation. We'll be talking a lot more about it later in the course. But you can start to get a feel for the kinds of things that you can do to augment your data. And in general, maybe the most important one is if you're looking at astronomical data or kind of pathology, digital slide data or satellite data, data where there isn't really an up or a down, turning on flip vert equals true is generally going to make your models generalize better. Okay, so here's the steps necessary to create our data bunch. And so now to create a satellite imagery classifier, multi-label classifier, that's going to figure out for each satellite tile what's the weather and what can I see in it. There's basically nothing else to learn. Everything else that you've already learned is going to be exactly nearly the same. Here it is, learn equals create CNN, data, architecture, right? And in this case, when I first built this notebook, I used ResNet 34 as per usual. And I found this was the case. I tried ResNet 50 as I always like to do. I found ResNet 50 helped a little bit, and I had some time to run it, so in this case I was using ResNet 50. There's one more change I make, which is metrics. Now to remind you, a metric has got nothing to do with how the model trains. Changing your metrics will not change your resulting model at all. The only thing that we use metrics for is we print them out during training. So here it's printing out accuracy and it's printing out this other metric called F beta. So if you're trying to figure out how to do a better job with your model, changing the metrics will never be something that you need to do there. They're just to show you how you're going. So that's the first thing to know. You can have one metric or no metrics or a list of multiple metrics to be printed out as your model's training. In this case, I want to know two things. The first thing I want to know is the accuracy, and the second thing I want to know is how would I go on Kaggle. And Kaggle told me that I'm going to be judged on a particular metric called the F-score. So I'm not going to bother telling you about the F-score. It's not really interesting enough to be worth spending your time on. You can look it up. But it's basically this. When you have a classifier, you're going to have some false positives, you're going to have some false negatives. How do you weigh up those two things to kind of create a single number? There's lots of different ways of doing that, and something called the F-score is basically a nice way of combining that into a single number. And there are various kinds of F-scores, F1, F2, and so forth. And Kaggle said in the competition rules, we're going to use a metric called F2. So we have a metric called F beta. In other words, it's F with 1 or 2 or whatever, depending on the value of beta. And we can have a look at its signature, and you can see that it's got a threshold and a beta. Okay, so the beta is 2 by default, and Kaggle said that they're going to use F2, so we don't have to change that. But there's one other thing that I need to set, which is a threshold. What does that mean? Well, here's the thing. Do you remember we had a little look the other day at the source code for the accuracy metric? So if you put 2 question marks, you get the source code. And we found that it used this thing called argmax. And the reason for that, if you remember, was we kind of had this input image that came in, and it went through our model, and at the end, it came out with a table of 10 numbers. Right? This is like if we're doing MNIST digit recognition. And 10 numbers were like the probability of each of the possible digits. And so then we had to look through all of those and find out which one is the biggest. And so that the function in NumPy or PyTorch or just math notation that finds the biggest and returns its index is called argmax. Right? So to get the accuracy for our pet detector, we'll use this accuracy function called argmax to find out behind the scenes which class ID, pet, was the one that we're looking at, and then it compared that to the actual and then took the average. And that was accuracy. We can't do that for satellite recognition in this case because there isn't one label we're looking for. There's lots. So instead, what we do is we look at, so in this case, So I don't know if you remember, but a data bunch has a special attribute called C. And C is going to be basically how many outputs do we want our model to create. And so for any kind of classifier, we want one probability for each possible class. So in other words, data.c for classifiers is always going to be equal to the length of data.classes. Right? So data.classes, there they all are. There's the 17 possibilities, right? So we're going to have one probability for each of those. But then we're not just going to pick out one of those 17. We're going to pick out n of those 17. And so what we do is we compare each probability to some threshold. And then we say anything that's higher than that threshold, we're going to assume that the model's saying it does have that feature. And so we can pick that threshold. I found that for this particular data set, a threshold of 0.2 seems to generally work pretty well. This is the kind of thing you can easily just experiment to find a good threshold. So I decided I would print out the accuracy at a threshold of 0.2. So the normal accuracy function doesn't work that way. It doesn't argmax. We have to use a different accuracy function called accuracy underscore thresh. And that's the one that's going to compare every probability of a threshold and return all the things higher than that threshold and compare accuracy that way. And so one of the things we would pass in is thresh. Now, of course, our metric is going to be calling our function for us. So we don't get to tell it every time it calls back what threshold we want. So we really want to create a special version of this function that always uses an accuracy of a threshold of 0.2. So one way to do that would be to go define something called accuracy O2 that takes some input and some target and returns accuracy threshold with that input and that target and a threshold of 0.2. We can do it that way. Right? But it's so common that you would kind of say, create a new function that's just like that other function, but we're always going to call it with a particular parameter. That computer science has a term for that. It's called partial, sort of partial function application. And so Python 3 has something called partial that takes some function and some list of keywords and values and creates a new function that is exactly the same as this function, but is always going to call it with that keyword argument. So here, this is exactly the same thing as the thing I just typed in. Act02 is now a new function that calls accuracy thresh with a threshold of 0.2. And so this is a really common thing to do, particularly with FastAI library, because there's lots of places where you have to pass in functions, and you very often pass in a slightly customized version of a function, so here's how you do it. So here I've got an accuracy threshold 0.2, I've got an fbeta threshold 0.2, I can pass them both in as metrics, and I can go ahead and do all the normal stuff. Find, quota.plot, finding with this slope, so I don't know, somewhere around on in 2, so we'll make that our loading rate, and then fit for a while with 5 comments less LR, and see how we go. Okay, and so we've got an accuracy of about 96% and an F beta of about 0.926, and so you could then go and have a look at Planet, leaderboard, private leaderboard, okay, and so the top 50th is about 0.93, so we kind of say like, oh, we're on the right track, okay, with something we're doing fine. So as you can see, like once you get to a point that the data's there, there's very little extra to do most of the time.
So when your model makes an incorrect prediction in a deployed app, is there a good way to record that error and use that learning to improve the model in a more targeted way?
Oh yeah, that's a great question. So the first bit, is there a way to record that? Of course there is. You record it. That's up to you, right? So maybe some of you can try it this week. You'll need to have your user tell you were wrong. This Australian car, you said it was a Holden, and actually it's a Falcon. So first of all, you'll need to collect that feedback, and the only way to do that is to ask the user to tell you when it's wrong. So you now need to record in some log somewhere something saying, this was the file, I've stored it here, this was the prediction I made, this was the actual, this is the actual that they told me, and then at the end of the day or at the end of the week, you can set up a little job to run something, or you can manually run something. And what are you going to do? You're going to do some fine tuning. What does fine tuning look like? Good segue, Rachel. It looks like this, right? So let's pretend here's your safe model, right? And so then we unfreeze, right? And then we fit a little bit more, right? Now in this case, I'm fitting with my original data set, but you could create a new data bunch with just the misclassified instances and go ahead and fit, right? And the misclassified ones are likely to be particularly interesting, so you might want to fit at a slightly higher learning rate, to make them kind of really mean more, or you might want to run them through a few more epochs. But it's exactly the same thing, right? You just pull fit with your misclassified examples and passing in the correct classification. And that should really help your model quite a lot. There are various other tweaks you can do to this, but that's the basic idea.
The next question, can someone talk a bit more about the data block ideology? I'm not quite sure how the blocks are meant to be used. Do they have to be in a certain order? Is there any other library that uses this type of programming that I could look at?
Yes, they do have to be in a certain order. They do have to be in a certain order, and it's basically the order that you see in the example of use, right? It's what kind of data do you have? Where does it come from? How do you label it? How do you split it? What kind of data sets do you want? Optionally, how do I transform it? And then how do I create a data bunch from it? So they're the steps. We invented this API. I don't know if other people have independently invented it. The basic idea of kind of a pipeline of things that dot into each other is pretty common in a number of places. Not so much in Python, but you see it more in JavaScript. Although this kind of approach of each stage produces something slightly different, you tend to see it more in ETL software, like extraction, transformation, and loading software, where there's kind of particular stages in the pipeline. So yeah, it's been inspired by a bunch of things. But all you need to know is kind of use this example to guide you, and then look up the documentation to see which particular kind of thing you want. And in this case, the image file list, you're actually not going to find the documentation of the image file list in Node Blocks documentation because it's specific to the Vision application. So to then go and actually find out how to do something for your particular application, you would then go to look at text and Vision and so forth. And that's where you can find out what are the data block API pieces available for that application. And of course, you can then look at the source code. If you've got some totally new application, you can create your own part of any of these stages. Like pretty much all these functions are, very few lines of code. Maybe we can look at an example of one. Image list from folder. So let's just put that somewhere temporary. And then we're going to go t.label from CSV. Then you can look at the documentation to see exactly what that does, and that's going to call label from data frame. So I mean, this is already useful. Like if you wanted to create a data frame or pandas data frame from something other than CSV, you now know that you could actually just call label from data frame. And you can look up to find what that does. And as you can see, like most fast AI functions are no more than a few lines of code. They're normally pretty straightforward to see what are all the pieces there and how can you use them. And it's probably one of these things that as you play around with it, you'll get a good sense of how it all gets put together. But if during the week there are particular things where you're thinking, I don't understand how to do this, please let us know, and we'll try to help you. Sure.
What resources do you recommend for getting started with video? For example, being able to pull frames and submit them to your model.
I guess the answer is it depends. If you're using a web, which I guess probably most of you will be, then there's web APIs that basically do that for you. So you can grab the frames with a web API, and then they're just images which you can pass along. If you're doing it client side, I guess most people are going to use OpenCV for that. But maybe people during the week who are doing these video apps can tell us what have you used and found useful, and we can start to prepare something in the lesson wiki with a list of video resources. It sounds like some people are interested. Okay, so just like usual, we unfreeze our model, and then we fit some more, and we get down to 9 to 9-ish. One thing to notice here is that before we unfreeze, you'll tend to get this shape pretty much all the time. If you do your learning rate find before you unfreeze, it's pretty easy. Find the steepest slope, not the bottom. Right? Remember, we're trying to find a bit where we can slide down it quickly. So if you start at the bottom, it's just going to send you straight off to the end here. So somewhere around here, and then we can call it again after you unfreeze, and you'll tend to get a very different shape. Right? And this is a little bit harder to say what to look for because it tends to be this kind of shape. We get a little bit of upward, and then kind of very gradual downward, and then up here. So I tend to kind of look for just before it shoots up and go back about 10x. Right? It's kind of a rule of thumb. So 1 in negative 5. Right? And that is what I do for the first half of my slice. And then for the second half of my slice, I normally do whatever learning rate I used for the frozen part, so LR, which was 0.01, kind of divide by 5, or divide by 10, somewhere around that. So that's kind of my rule of thumb, right? Look for the bit kind of at the bottom, find about 10x smaller, that's the number that I put here, and then LR over 5 or LR over 10 is kind of what I put there. Seems to work most of the time. We'll be talking more about exactly what's going on here, what discriminative learning rates, as the course continues. So how I'm not going to get this better than 929 because there are how many people in this competition? About 1,000 teams, right? So we want to get into the top 10%. So the top 5% would be 0.931-ish. The top 10% is going to be about 929-ish. So we're not quite there. Right? So here's the trick, right? I don't know if you remember, but when I created my data set, I put size equals 128. And actually the images that Kaggle gave us are 256. So I used the size of 128 partially because I wanted to experiment quickly. It's much quicker and easier to use small images to experiment. But there's a second reason. I now have a model that's pretty good at recognizing the contents of 128 by 128 satellite images. So what am I going to do if I now want to create a model that's pretty good at 256 by 256 satellite images? Well, why don't I use transfer learning? Why don't I start with the model that's good at 128 by 128 images and fine-tune that? So I don't start again, right? And that's actually going to be really interesting because if I'm trained quite a lot, if I'm on the verge of overfitting, which I don't want to do, right? Then I'm basically creating a whole new data set effectively, one where my images are twice the size on each axis, right? So 4 times bigger. So it's really a totally different data set as far as my convolutional neural network is concerned. So I kind of going to lose all that overfitting. I get to start again. So let's create a new learner, right? Well, let's keep our same learner, but use a new data bunch where the data bunch is 256 by 256. So that's why I actually stopped here, right before I created my data sets. Because I'm going to now take this data source and I'm going to create a new data bunch with 256 instead. So let's have a look at how we do that. So here it is. Take that source, right? Take that source, transform it with the same transforms as before, but this time use size 256. Now that should be better anyway, because this is going to be higher resolution images. But also I'm going to start with, I haven't got rid of my learner, it's the same learner I had before, so I'm going to start with this kind of pre-trained model. And so I'm going to replace the data inside my learner with this new data bunch. And then I will freeze again, so that means I'm going back to just training the last few layers. And I will do a new LR find. And because I actually now have a pretty good model, like it's pretty good for 128 by 128, so it's probably going to be like at least okay for 256 by 256, I don't get that same sharp shape that I did before. But I can certainly see where it's way too high, right? So I'm going to pick something well before where it's way too high. Okay, maybe 10x smaller. So here I'm going to go 1 e negative 2 over 2. That's, seems well before it shoots up. And so let's fit a little bit more. Okay, so we froze them again. So we're just doing the last few layers. I fit a little bit more. And as you can see, I very quickly, remember kind of 928 was where we got to before after quite a few epochs. So we're straight up there, and suddenly we passed 0.93. Right, so we're now already kind of into the top 10%. So we've hit our first goal. Right? We're at the very least pretty competent at the problem of recognizing satellite imagery. But of course now, we can do the same thing before. We can unfreeze and train a little more. Okay, again, using the same kind of approach I just tried before, allow it 5 here, and even smaller one here, train a little bit more, 0.9314. So that's actually pretty good, 0.931. Cool. Somewhere around top 20-ish. So you can see actually when my friend Brendan and I entered this competition, we came 22nd with 0.9315, and we spent, this was a year or two ago, months trying to get here. So using kind of pretty much defaults with minor tweaks and one trick, which is the resizing tweak, you can kind of get right up into the top of the leaderboard of this very challenging competition. Now, I should say, we don't really know where we'd be. We actually have to check it on the test set that Kaggle gave us and actually submit to the competition, which you can do an exhibition. And so later on in the course, we'll learn how to do that. But we certainly know we're doing well. We're doing very well. So that's great news. And so you can see also as I kind of go along, I tend to save things. You can name your models whatever you like, but I just want to basically know, is it kind of before or after the unfreeze, kind of stage 1 or 2, what size were they training on, what architecture were they training on. So that way we can always go back and experiment pretty easily. So that's Planet, multi-label classification. Let's look at another example. Enough of the other example. Next we're going to look at is this data set called Canvid, and it's going to be doing something called segmentation. We're going to start with a picture like this, and we're going to try and create a color-coded picture like this, where all of the bicycle pixels are the same color, all of the road line pixels are the same color. All of the tree pixels are the same color, all of the building pixels are the same color, the sky is the same color, and so forth. Okay? Now, we're not actually going to make them colors. We're actually going to do it where each of those pixels has a unique number. So in this case, the top left is building, so I guess building is number 4. The top right is tree, so tree is 26, and so forth.
All right, friends, so I managed to record the results, run all the results, and I promised I'd walk you through them, so I'll go ahead and do that now. I'm not connected at the moment because I don't have the instance running, But I did run the results, and you can actually see what that looks like. And so when I ran this the first time, I was able to get about 92%, 92.4% F beta, which is the criteria that we actually care about. And then when I ran this again, after a little bit of optimization, I was able to get 92.9. So up to 92 point, that is actually world class. That'll rank us way up there in the list of so 92.9 has us at about 89, so top 10% on Kaggle. Although this was about 2 years ago, so I'm gonna get too excited about that result. But anyway, so this was even before we went into this 256 action. So this was just using 128 by 128 size images. And so I'm pretty sure like with 256, we could have gone well up to into the 93s, maybe even touch 94. I don't know, like that's certainly possible. But when I did try to run this, I got this error and I didn't really look too deep into it. Queued out of memory. I think I would have needed to reduce the batch size, but I hadn't. So just cut down the batch size to make it smaller because we are running 256 images now. And so that's something I'll do later. But what I want to do now, or next, is really get the syntax down. So really understand what's going on with the transforms and data bunches and all of these, and have the opportunity to mess around with that more. And so I'm going to build an app. I don't know what the concept is going to be, but I'll figure out how it's going to work, and I'm going to build it and deploy it. And then in the process, just learn a lot more about the syntax, and also disclose this little top tip that I use whenever I try to memorize things long term. And so I'll dive into a little bit about what that is and how you can use it to improve your memory tremendously. But all that coming up in the next video. So I'll do that, and then we'll come back to lesson 3 and take it away with Jeremy to see how much more we can learn, all the awesome stuff that we can do with deep learning. So that's it for now. I will see you guys in the next video. Adios.